Let's go already. Like how you do with the digital version first, because yeah, going on, and you're the only one who hasn't received the book in 5 weeks. Okay, anyways, let's begin. Good, Melvin. I see you have done the homework. Good, excellent. I think we went through the ABCs already, right? Have we gone through the ABC discussion yet? No. Oh, okay. Check answers, boys and girls. Can you guys check answers real quick for this one? Just check answers. Then mark down whichever one that you did not get your correct one. Question number 5, the first one is supposed to be donkey. The second one, 6, is supposed to be boy. Question number 8 is supposed to be boy. Question number 9 is supposed to be A. Question number 10 is supposed to be A. And question number 11 is supposed to be donkey here. Most of you guys would get question 11 wrong. I'll explain later. Question 14, faster with donkey than 14. Next page. 14, 14 is supposed to be donkey, guys. Yeah, right. There's obviously A, B, C, D, right, in the multiple choice. Question 14, donkey. Question 15, C. Question 16, donkey. Question 34, C. Question 35, A. Question 39 is supposed to be donkey, and question 40 is supposed to be donkey as well. Guys, besides question 11, is there any other question or not? Let me go through question 11 first, since some of you guys may be a little bit confused with this chapter here. Guys, for those who got question 11 wrong, you first and foremost is basically going back to the understanding of what will be generated when there is a current flowing here. You know for a fact that when there is a current flowing here, right, then this thing here will become an electromagnet, right? And if it becomes an electromagnet, usually one side of it will be the North Pole and one side of it will be the South Pole, right? If you look at all these other magnetic field lines, no way you're going to get magnetic field line like this, right? The only way you can get magnetic field line like this is if you have like a north here and then you have a south here, then okay, possible for you to get a magnetic field line like this. So A is out of the question. B is like a very, very special kind of situation. It doesn't make sense at all. Like there's no scenario for that. And C is the only possible way is if there is a north here and there is a south here, then it could be possible that here, but that won't explain these magnetic field lines also. The only answer here is actually donkey, which the D was missing, but it's actually there, right? But essentially, think about this way. This is the north and this is the south, right? So the magnetic field line will go out here, they'll come back into here, and then they'll go into the south here, right? So you're supposed to imagine how the magnetic field line is for these kind of scenarios. You get what I mean or not? So donkey is definitely the answer here. Any other questions that you guys got wrong for this part here? Could you scroll up again to the answer? Yeah, sure. Any other questions, guys, while Raj is checking his answers here? Any one of you guys got a different answer or not? Okay. Everyone got everything else correct, huh? Yes or no? Yeah, the door has been spoiled for like a while already. You can just push the door. Okay. Okay, everyone. Then we move on to the next part if there's no questions. Right. Okay, then after that, this part here is essentially going to be the paper 4 questions already, right? First and foremost, they ask you, state the relationship between the resistance R and the length of a wire of constant cross-sectional area. What's the relationship between R and L? Every time you ask these kind of questions, you want to first put the formula for resistance of a wire to the side first. R is equal to L over A, right? If you remember this one, R equal to L over A here, then obviously you can state your relationship. Resistance should be directly proportional to L, and resistance should be inversely proportional to area, right? Which builds your answer for these questions already, right? Resistance is directly proportional to length of wire. Or you want to say R is directly proportional to L is acceptable as well. And I ask you the cross-sectional area here, right? Then resistance is inversely proportional to the area. Okay, easy. Then you get only 1 mark because it's essentially the same thing. Yes, everyone must know this. Hey, this formula is very, very important, as I've mentioned last week. If you don't get this formula right, you'll get everything wrong. Okay. Then moving on to the next part. A 60-watt filament lamp is connected to a 230 volts. This is always label your information, guys, because it's going to get hectic later on. Then after they ask you to calculate the current, you have power, you have voltage, you are asked to find current. The only logical formula that will equate all these 3 things together is the power formula, right? Which is equal to VI. From here, if you're looking for the current formula, your I will be essentially P over V, right? Which in this case here will be 60 divided by 230 here. Press that in your calculator and you'll get 0.26, is it? Oh, sorry, 0.23 or 26. 0.26 amperes. Correct the 2 significant figures. But of course, you can press it into your own calculator and double check if this is correct or not, because I'm just looking at someone else's answers. Right, you're supposed to get 0.23, or you can write up to 3 significant figures, guys. But always remember to write your units, because if you don't write your units, it is absolutely wrong. Okay, then this next question here is a 4-mark question, which is quite a lengthy question. Guys, see what they want from you. Lamp Y has a filament made of the same metal. If they are the same metal, I don't care about the resistivity anymore, right? Because if you remember, guys, the formula is actually resistivity times length over area. But I've mentioned last week, guys, that we usually don't care about the resistivity because they are usually the same metal, okay? So this one here is one key information. It's filament in lamp X. This filament has half the length and 1/3 the cross-sectional area of the filament in X. Okay, so imagine if, let's say this is the first wire, right? It had length L and cross-sectional area A. Right now, this second filament, they say it's half the length and 1/3 the cross-sectional area, guys. Right now, this thing here is half the length and this is only 1/3. So it's like area over 3 only, guys. Right? And then they say that lamp Y is also connected to a 230 volt power supply. They're asking for the current here. I don't know what the current is, but I know for a fact that I can find the resistance here first, right? How do I find the resistance here? Using this information, right? I have voltage right now, and I also have the current here. According to my Ohm's law formula, if I do the V equals to IR formula, my R will be essentially 230 divided by 0.26. Divided by 0.26, right? Press this in your calculator and how much you will get in terms of resistance? 800 over, so big. Is it? All right, give me a calculator. Okay. 884.6 ohms. Once I have this already, then it's very easy to do already lah, right? Because yet again, I'm just comparing the length to the length and the area to the area, right? If I halve my length, what will happen to my resistance? Wait, what will happen? If I halve my length of the wire, what will happen to the resistance? Good, you'll half as well. So from this length itself, I go 884.6 divided by 2, right? Which is going to give me 442.3 ohms, right? This is just comparing the length first, Then after that, I compare the area here. If I divide my area by 1/3, what would happen to my resistance? Times 3, excellent. So by comparing the area, 422.3, I need to multiply it by 3, right? Which will give you 96231. Is it 1326.9 ohms? Do you all get that? 1326.9 ohms, right? Then now I have the resistance already, right? I want to calculate how much current is in Y and X, right? Just now in X, we already calculated the current to be 0.26 already. Right now, I want to find the current in Y only by using, yet again, Ohm's law, yet again, V equals to IR. My R will be once again V over I. Oh, sorry. What my I will be V over R, right? Which in this scenario here will be 230 volts again, because they stated here is 230 volts, right? Divided by my resistance 1326.9. Press this into my calculator and you'll get what? 0.17. 0.17 amperes. Right. So this guy here gets 0.17 amperes and this guy here gets 0.26 amperes. Then it's just a ratio already, all right. If you want to do the ratio, it'll be like 0.17 divided by 0.26. 0.17 divided by 0.26, you'll get a very weird number. You'll get somewhere around 0.65. Somewhere around there. But if you use 3 significant figures, it will be a different value. In fact, if you use 3 significant figures all the way, you'll get 2 over 3, which is 0.66666666666. So if you got somewhere around here, it's actually correct already, guys. But before, yeah, if you do 3 significant figures, it will be more accurate. It will be more accurate, but it's because right now here I already use 2 significant figures only. And here I just follow back along. Here I follow back 2 significant figures. Then I get 0.65 lah. But if you did 3 significant figures and 3 significant figures, you'll get 0.66666, which is the same as 2 over 3. So if you got somewhere around here, it's okay already. The working is more important than the final answer, guys. Your ratio should be 0.66, around there, 0.66. Anyone don't understand this part? Anyone lost in the woods? Hey, very good, you did this correct. Did you do this question correct? Did you attempt this question? 你有做好功课吗？你有做好功课？你 Okay. All right. Anyone need me to repeat this? Does everyone understand what I'm talking about? It is an important chapter, guys. You will see this along with. Okay, but good job. You actually did it. I'm proud of you. Okay, if there's no questions, then 2/3 is supposed to be your answer. Copy everything down as much as you can. This is actually just the final step, right? This was your first working here. This is your second working here. And this is your third. Naming by right? You understand what's going on now? You need to know this one. Very, very important. Your answer should be 0.66 or somewhere near there. Okay. Next. Okay, then moving on to the next question. This next question is a relatively easy question, but first things first is I want to ask guys, does this lamp have increasing resistance or does it have decreasing resistance? Alvin, what do you think? Does this lamp have increasing resistance or decreasing resistance, and why? Did you right? Yeah. Increasing or decreasing, and why? Increasing. Good. Why? What do you mean it goes up? It's going towards the right wall. Why is it still increasing resistance? It's still increased now. What the hell? Wait, last week I taught you guys this, right? I taught you guys the ohmic conductors, right? This one here goes up one or why this one now go down is still increasing resistance? Why? Wait, you did it one or you chinchai tembak one. Abigail, tell me why. Why? Why this one go up? I say increasing resistance. I mentioned this 2 weeks ago, right? Remember, right? Right, a non-ohmic conductor. I said it's a filament. I said it's a filament lamp, right? Do you remember or not? Yes, right? Okay. Then right now my question is why this one here, even though it's tilting towards the right, it's still increasing resistance. Sorry, what do you say? The resistance is consistent. That's why the resistance is increasing. Why this one is increasing resistance? What do you mean proportional? What the? Wait, how do you get the answer?
Just we input by arm and then you calculate the small one and the up one.
Oh, okay, good. That's one of the ways to do it. Yes, that's correct. Very good. What do you want to say? Guys, let me tell you why this one is increasing resistance, okay? In fact, I mentioned this 2 weeks ago. I said that in a normal scenario, if you think back about the Ohm's law formula, R is equals to V over I, right? Right. The reason why my graph was curving up like this is because this here was V and this one was I. If I look at this graph here, you can see that it actually increases towards the V direction here, right? And I know for a fact that mathematically, increase in voltage more than the increase in current will increase the resistance. For example, numerical value is 10 divided by 2 versus 20 divided by 3, right? You can see that the increase in voltage is more than the increase in current, right? And because of this one would have been 5 ohms, this one would have been 6.66 ohms, right? You can see that this is clearly an increase in voltage more than the increase in current, thus increasing your resistance. This is true if I have a V versus I graph. But if you look at this graph here, this is a I versus V graph, guys. And because once again, this lamp here is tilting towards the V direction, this indicates that the increase in voltage is more than the increase in current, guys. And thus, And thus, this one here has increasing resistance. This one here will have constant resistance. Make sure you know, right? Yes.
Very hot lah. Very hot.
Go get the aircon control outside. Flip it until it's 17 here. Where's the aircon control? Now it's in that room. Go ask Kenny. Go ask Kenny. After you're hot, right? Go. Not hot, I told you. Man, I'm all right. You're hot, go get it. Seriously, I'm go get it. So if it's a V versus I graph, then an increase in, if it tilts up like this, it means to say that it increased the voltage more than the current. But if it's an I versus V graph here, right, if it tilts this way, it means to say the voltage is more than the current. Yes, 17 is the maximum, sadly. Okay, everyone understand now? Especially those who are online, please make sure you understand, guys. All right, then from here, it's just a matter of writing down all the information already. The resistor definitely has constant resistance because it has a constant gradient, right? Then the lamp will have increasing resistance. Stays the same. You mean like? Oh, yeah, you can. Yeah, you can. And this one here is just a matter of 7 volts, guys. You can literally find it from the gradient. You know how to find this, right? Just use the V over the I times the R. Okay, what the hell? Oh no, this one is not it. This one is the same resistance. Same resistance means to say this point here, guys. This one here is the same resistance, which is this same point here, which if you scroll down, it's just going to be 7 volts. Easy. And you get your free 3 marks already. Okay, all right. Okay, good. Thanks.
It's not 7.
It is. This part, you know, is called, it's the same resistance, right? It's the same resistance because they get the same voltage and the same current. So you just need to like literally draw downwards only. Then you'll see that it is actually going to be 7. Half, Nani. This is the intersection point, right? Let's scroll all the way down here. Good. Okay, next. Easy. Another, oh, this one is one of the other harder questions here. How much do you get? Wrong. Wow, very close, but wrong. Alright guys, this one here is also one of the harder questions from last week, guys. If you look at this information here, it says that a coil of wire is connected to a circuit containing a variable resistor, means the resistance changes, and a battery. The variable resistor is adjusted until the potential difference across the coil is 1.8 volt. This is obviously your voltage. In a current with the circuit 0.45 amperes, this is obviously your current lah. First and foremost, it asks you to calculate the resistance. Super easy, super straightforward. Literally, just use the Ohm's formula once again. V equals to IR. Your R will be equal to V over I. Right, and literally just put in the numbers, and you'll get a very easy answer of 4 ohms. Right. Oh, by the way, a pro tip number 1, guys. When you get something like 4 ohms, right, you need to like 4.0. But they don't really emphasize on this far, right? I noticed that some of the mark schemes they don't allow for 1 significant figures. So you actually need to make it 2 significant figures, as I keep saying over and over again. 2 significant figures, but they don't really emphasize on this. So I have a hunch that they actually let you slip off with this, but it's good practice lah, right? To write 4.0. OHMS can also, but not recommended, because you are supposed to write the symbol. Ohms is the word, right? This is the units, right? So like we won't write 1.8 voltage here, right? But we will write 1.8 V, which indicates that it is voltage. Yeah. So it's not wrong, right? But it's not recommended. Okay. And then the next part, the thermal energy, which a lot of people actually get confused, because whenever they talk about thermal energy, straight away they'll think about Q equals to MC theta, right? Now this formula is definitely not wrong, guys, but in this situation, it is definitely the wrongest of the wrongest. Why? Because you don't even have the information here. You don't have mass, nor do you have specific capacity, nor do you have change in temperature. However, the information you have here is going to be the same thing here. You still have voltage, you still have current, but right now you have time. And the only formula that relates voltage, current, and time is essentially the E equals to VIT formula, right? Right. Which means to say you're actually supposed to do this. You're supposed to do like 1.8 times with 0.45 times with 9. Is it? Do I times 9 here, Shen?
No,
Why not?
it's in second.
Good, excellent. So you're supposed to multiply it in seconds as well, guys. And thus, you know, press that in your calculator and you'll get a very big number. I think it's 2160. Right, assuming Melvin is correct. Hey, wait a minute. Why is it in watts? Wait, you're looking for what?
Joules.
Sorry, what do you say, Leo?
Look for joules. The energy for the measurement for energy is joules.
Yeah. Yes, excellent job. That is absolutely correct. It is supposed to be in joules. 437. Wait. And thus, bloody hell, VI is 4 ohms. Are you sure? Yeah, it's because I trusted the wrong guy. 1.8 times 0.45 times 9 times 60. Yes, you're supposed to get 437 joules instead, not 210. No, you cannot, because you can only write up to 3 significant figures. As I've mentioned 1,000 times. 437, bro. 这个明明是 V over R， V over I， 周末突然之间会变到另外一个答案呀？你跟我讲。Right. Okay. Right. Then this last part here. How many of you guys attempted this? Leo, did you do this? Raj, did you do this as well? Wait. I'm assuming no. What do you get? No, you didn't attempt it as well. You were? 没有做过功课. You're the model student of the week. Okay, anyways, look at this question here, guys. This question here is once again the formula that relates to R equals to L over A formula, guys, but there is obviously a huge twist here. This one here, some of my students were struggling in the Wednesday class also, so please pay attention. It says the coil in part A is replaced by 1 meter of wire. 1 meter of wire which has half the diameter. It's half the diameter, not half the area, half the diameter. And we know for a fact that when you half the diameter, what will happen to the area? What will happen to the area? Divide by 2 also, is it? Will it be half the area? Or will it be a quarter of the area? Which one will it be? It will be a quarter because of the square component. So I know for a fact that this is like a quarter of the area. Okay. Now it says that when the potential difference across the coil is again adjusted to 1.8 volts, the current right now is 0.3 amperes, right? And they asked me to calculate the length of the wire in the second coil compared to the length of wire of the first coil. Now, all this may sound a lot like gibberish, and truth be told, when I read this the first time, I had to read it the second or third time only to understand what the question wants from you. Let's dissect it one part at a time. It says that right now the coil in part A is replaced by the other one, which is half the diameter, right? So let's assume that this wire here, right? This wire here, I don't know how long it is and how big the area is, but if I were to draw it out in terms of illustration, let's say that initially it has a length and area, right? This is the baseline. And then I fed it with 1.8 volts and 0.45 amperes. I fed it with 1.8 volts and 0.45 amperes. And I know that this thing here had 4 ohms. Okay? This original first wire had 4 ohms. We all know this, right? Then after that, the second wire, which has half the diameter, which will a quarter of the area here, guys. It will a quarter of the area here because, like I've shown you last week, when you half the diameter or you half the area, it will actually quadruple down the area, right? What did I say? I repeat this again. When you half the diameter or you half the radius, the area will quadruple down, right? If you don't know, go back and watch the video from last week again, right? Then after that, they say that
Half the diameter.
you half the diameter or half the radius, the area will quadruple down. Means to say it will become a quarter of the original area. You can do this on your own mathematically, guys. Go prove it for yourself, like how I showed you guys last week, right? Then right now, the second wire here has 1.8 volts and it has 0.3 amperes. Okay, if you draw all this out, right now you know what to do already. So first and foremost, I need to find out how much resistance this is, right? So if I use the Ohm's law formula, which is V equals to IR, once again, my R will be equals to V over I. Everything else is not important really. V over I, which will give me 1.8 divided by 0.3, which is going to give me 6 ohms. Okay, so I know for a fact that this thing here is 6 ohms. Yes. Can we, everyone follow right until here? 6 ohms, everyone understand? So this wire is 4 ohms and this wire ultimately should be 6 ohms. Then they asked me to calculate the length of the wire, right? I don't know what length this is. I don't know, right? But I know for a fact that when I compare the area here, when I divide by 4, guys, the area, what happens to the resistance?
Times 4.
Times 4. So the first information I know is that by right, my 4 ohms should be multiplied by 4 because here divide by 4, right? You give me 16 ohms. By right, if I just compare the area itself, this is just the area itself, my resistance of the wire should be 16 ohm, right? But I don't want it to be 16 ohm because the information gives me that ultimately this wire should be 6 ohms only. So the next question I ask myself is, if this thing multiplies by this thing, I don't know what it is, right? It's supposed to make my wire, it's supposed to make my wire from 16 multiply by whatever it is, I don't know. It's supposed to ultimately give me 6 ohms only, right? Because I know for a fact that the length of the wire must be shorter, right? In order to decrease the resistance right now, right? The length of the wire right now should be shorter than the original one to decrease the resistance, right? So I ask myself, multiply by what becomes 6? It's just algebra at this point, right? It will be essentially 6 over 16, right? Which is 3 over 8, right? Yeah. You guys know what I'm talking about, right? It's basically 6 over 16, which is going to be 3 over 8. Meaning to say my length should multiply 3 over 8 to get to 6 ohms, right? Which means to say, in other words, this should be 3 over 8, the original length of the first wire, right? Right, which means to say my final answer here is going to be 3 over 8 lah. Length of the y in the secondary column is 3 over 8 the length in the y of the first column. Because if this was original L length, then this must be 3 over 8 L1. You guys understand what I'm talking about, wait, guys? This one here is a little bit complicated. I'll copy everything down. How do you get the 6 ohms again? By comparing the voltage and current here. 1.8 divided by 0.3, I'll get the 6 ohms. Yeah.
What is the times?
Which one?
3 times 3.
Because originally, I don't know how much is the new length, ma. I don't know how much is the new length, right? But I know for a fact that by just comparing the area, the resistance becomes 16 ohm already, right? But I know that the final resistance of the wire should be 6 ohm. So it means to say, if this thing is like 100 meters long, this thing should be shorter, right? This thing should be shorter. By how much shorter? I don't know. But I know for a fact that if it is shorter, right, then I should, this thing, this L multiplied by something should be this new one, which means to say this 16 ohm multiplied by something should be the new 6 ohms in length. Wow, I think you're going to get even more confused right now already. Okay, I start from here. So right now we established that this thing here is like 4 ohms and this thing here is like area and length, right? The new one, we know that it's half the diameter, right? So I know that it's going to be a quarter of the area, right? This part here, right? So if it's quarter of the area, first I compare the area. Here to here is a divide by 4, right? Then I know that it's going to be like 4 multiplied by 4, which is going to be 16 ohms, right? But this wire here at 1.8 volts and 0.3 amperes. So this wire should only be 6 ohms only. This thing here should only be 6 ohms. So it means to say my length must decrease also, right? What's my new length? I don't know. I don't know what's my new length, but I know for a fact that my 16 ohm multiplied by this multiple here. Let's not call it y. Let's call it y. Right, multiplied by y should make the y only 6 ohms only. Right. So my y should be 6 over 16, which is going to be 3 over 8, which means to say my L should multiply it by 3 over 8 to become 6 ohm. Because originally it was 16 ohms, so I'm just comparing the area. Do you understand?
3 over is the length.
No, yeah, 3 over 8 is the new length. If this one was like, if this thing was like 80 meters here, then this thing here should be 330 meters. Because I only can have 3 over 8 of the multiple only to make it from 16 ohm to 6 ohm. Why is he here? There's no maths class though. He's here for online maths class. Hey, you know there's no maths class right today? You know Gilbert is not here, right? Yeah, Gilbert is not here today. Do you know or not? It's replacement. Who's replacing? He said online, Maybe that's the reason why some of the students are not here so today. Okay, everyone understand this? It's a very difficult question, I must say, but it's doable one, step by step. Okay.
Say this replace.
Can you be replacing the maths class? Maths class 是有 Chinese 啊。What? Okay, then the final question here, before we move on to the next chapter, is a simple chapter here, right? So first and foremost, it says that figure 8.1 shows a high voltage supply connected across two metal plates. So this is high voltage supply represented by the plus and minus here, and it's connected to two metal plates. This one here will obviously be positive, and this one will obviously be negative, right? Explain what is meant by an electric field. Now, guys, and you see that this simple explanation requires 2 marks. Yes, and I can see some of you guys have already left it empty already. Good. But if you recall of exactly what I mentioned a few weeks ago, you'll notice that when we went to the electric field chapter, I actually gave you the notes and answer for this already. I put this here specifically because I said that in your exam, they like to ask this question. Where God?
2 sentences.
It's the same thing. Both of it is the same thing. An electric field is a region in which an electric charge experiences a force. Remember, I told you, right? There's no such thing as an electric field. And because there is no such thing as electric field, it's made up. So how did the scientists make this up? They place a very small positive charge here and they observe what force was acting on this, and you know for a fact that positive and positive are going to repel, right? So that's why one positive charge moved this way, one more positive charge moved this way, one more positive charge, one more positive charge, blah. And this gave rise to the electric field. It's the opposite. The opposite is true as well. If I put a small positive charge here, obviously it will be attracted towards the negative, right? And that's why this gave rise to the electric field. So electric field is a made-up thing. There's no such thing as an electric field, right? It's made up. That's why you see the explanation here. It says that electric field is a region where an electric charge, which is that small positive charge, experiences a force. Or you can even say that direction of an electric field at a point is the direction of the force on a positive charge at that point, which explains my concept just now. You can write either one of this and you will still get your mark. You must mention the electric charge and you must mention that it has a force acted on it. These are the keywords. You can mention that it is a positive charge, but even if you write electric charge, it's good enough already. So the keyword is the charge and the force. You must mention that this positive charge experiences a force, and then you get your marks. Soothing ringtone. Please. Okay. Then finally, okay. Then after that, they ask you to draw electric field lines between the plates and indicate the direction with an arrow. Why this one you don't know how to draw, man? The electric field plates, wait, this one is positive and this is negative, right? What I want you to do is you draw at least 3. My recommendation is draw 4, which are equally spaced between each other. You don't draw like one like this, then other one like this. You don't do that, all right? You must draw them equally spaced towards each other, and then at the end here, you can even draw like the curving circular ones, which is essentially what I drew on the first page of the electric charge chapter, right?
That's wrong.
Not a must, but recommended. Right. And finally, oops, not finally, yet again, you have this charge, which is your Q. You have this T, which is your T. You're looking for the ammeter reading, which is obviously your I. Oi! Look at Shopee, bloody hell. Huh? What do you get for this one? 0. You're supposed to use the Q equals to IT formula, guys, and obviously your Q over T will be equal to your I, right? Which in this case here will be 0.06 divided by 30. Press 10 in your calculator, and then you're going to get a very small number, 0.002 amperes. Okay, easy. And finally, they ask you to find energy once again, and they already give you these dead answers already. Literally, just substitute it into your formula and press it into your calculator. And you'll get watts again. Bloody hell. How much? 120 joules. Wow, 这么你会拿到40的喂 How do you get 4? Fair enough. Anyone got any questions with this part here?
Joules, right, 110.
Yes, all energy is measured in joules. Okay. Good. Now, looking that we have so much time, right? Most likely we can do another chapter, which is going to be this chapter here. Okay. If you look at this next chapter here, guys. Wait. Okay, if you look at this next chapter here, you'll see that the first page here is basically the symbols for each and every one of the relatively more important components, right? If you look at this first part here, it's quite common sense, right? You know all these things are, these are cells and batteries and whatnot. This is a direct current, this is an alternating current, guys. Probably the only relatively more important ones here is this one and this one. The AC and the DC symbol. Make sure you know this, right? Then after that, the next part here is basically a potential divider. These two are potential dividers, and this thing here is a heater, guys. This one here is relatively important as well. The next part here, you'll see that there is fused, fixed resistors, variable resistors, and thermistors. I would say all three of these are relatively important. Put a little star on the side there, right? Then you have a light-dependent resistor, which sometimes is drawn with a circle and sometimes is drawn without the circle. Both of these are the same thing, guys, just that it is with and without the circle only, but they are the same thing. This one is definitely important. A diode is also important. Most of the time, you'll see that it's not drawn with a circle for diodes, especially in your IGCSE syllabus. And this is a light-emitting diode, guys, which the main difference between this and this is that the lights are actually, this one is emitting light, right? That's why the arrows are pointing outwards. this light dependent resistor is actually receiving light. That's why you can see that the arrows are pointing inwards, guys. And then here is a transformer, bell and buzzer. You should know. Oh, you'll learn this later on in the chapter, but just know that this symbol is important for now, right? Then these are basically relays and magnetizing foil, which is not so important. Now, guys, for those with the little stars on the side here, guys, why did I put a little star here on the side here is simply because you will be asked in your exam, guys. Most of the time, you'll be asked to draw the circuit symbols in your paper 6 questions, and occasionally in your paper 4 as well. And most of the time, I see the students, they will always forget these few symbols here, which are very commonly asked in your exam. So if you don't want to memorize anything, at least you memorize the ones that I put in the star there. Those will definitely come in handy once in a while. And if you're lucky enough, it'll come in really handy in your exam. The prophecy. Okay. Okay, then yeah, this one here you can just read it for yourself, or just when you find yourself, oh shit, I can't remember the symbol of blah blah blah, right? Just refer back to this page. It is more than enough to help you get through most, if not every one of the questions that requires you to draw a symbol. Make sure you know this. They will ask you, they will test you this, right? Then the next part here is essentially just the series and parallel circuits here, right? In terms of your series and parallel circuits, you must understand how the flow of current is and how the distribution of voltage is, depending on whether it is a series circuit or also a parallel circuit. And in order to understand this, yet again, I would like to share you a very simple story of mine. Let's imagine today, right? It is someone's birthday party. Let's say it's Melvin's birthday party, right? And you can see from the facial expression of his face, he is filled with pure joy and happiness already, because it's his birthday, right? And in his birthday, he can only choose to invite 4 of his friends only. So, number 1, obviously, he's going to invite me, right? Because I'm his favorite physics teacher, right? Then he's going to invite one of his best friends from school. And then maybe he'll invite his girlfriend also, if he's not gay. But if he's a boyfriend, it's also acceptable, right? Because in the new society, we don't judge, right? No homo, right? But anyways, they're all very happy, obviously, right? And so if let's say there's a birthday party going on, and all of us, as tradition, will obviously buy a piece of a cake, right? On this cake here, it's written it's decorated very nicely already. It says happy birthday. With obviously arts and blah blah blah, right? Then okay, so if let's say imagine today there's a piece of cake here and there's 4 of us, because this is the important part, everyone pay attention now. If there is a cake here and there is 4 of us, because all of us are of equal status, right? None of us has a VVIP status here. So what happens is, if we have a piece of cake, we will separate it into 4 exact pieces. Melvin will get a piece of the cake. I will get a piece of the cake. Your best friend will get a piece of the cake, and your girlfriend or boyfriend will get a piece of the cake. Right? This is in a normal scenario. Okay. But what if suddenly someone very, very important walks in? Someone very, very important, which could be the next Prime Minister of Malaysia. Who is the next Prime Minister is going to be? Who is it? Who is it? Okay, let's imagine it's Anwar, right? With his little mustache here. Obviously, he's happy, right? Because he's going to become the Prime Minister. So if let's say the Prime Minister, what's it called? With a little bit ill manners, they actually decided to crash into our party. And then, yet again, we have this piece of cake here. Do you think we'll still distribute the cake equally right now? This guy here is VVIP status soon already. In fact, might be even the Prime Minister already. PM number, what is it, 11? I don't know, something. It's very, very loose already, the political scene in Malaysia. But let's say it's PM 11 here, right? And because Anwar is here right now, and he is obviously of a different status quo, then right now the cake will be distributed differently, all right? Maybe out of courtesy sake, we'll say that, hey Anwar, you take this cake lah for serving Malaysia. Finally, congratulations, and you finally get to become the Prime Minister already after going to jail, being accused of butt sex and whatnot, right? But he's finally Prime Minister. Then because the rest of us are peasants, right? We'll still get the equal amounts of cake on Melvin here, me, the best friend, and also the girlfriend. Okay. This scenario here is essentially how series voltage works, guys. You must always remember that SVC, which is the keyword here, guys. SVC, series voltage, is that piece of cake. Okay. So how will the both scenarios go then? Imagine today, right now, all of us are equal status, right? So right now, let's say that I have a battery here, which provides 9 volts of current, 9 volts of voltage. I have one resistor here, another resistor here, and also another resistor here. Let's assume that all of them are equal resistance, which is the first scenario, right? All of us are equal status. If we're all equal status, how much cake will this guy get? How much cake will this guy get? And how much cake will this guy get? How much? 3 volts, 3 volts, and also 3 volts. The cake series voltage is the piece of cake, by the way. The cake will be distributed evenly, right? And when the cake is distributed evenly, let's imagine the second scenario. Then Anwar walks in already right now. Anwar walks in, big guy, right? So how will the distribution of the cake be right now? How much voltage will this guy get, and how much voltage will this guy get? The bigger resistor, guys, like the bigger VIP, will always get the bigger piece of the cake, right? So this guy here will right now get 3 volts, and this guy here will right now get 6 volts. 6 and 3 volts, the distribution will be different already, guys. And because of this, we can actually formulate the formula that voltage total is equals to V1 plus V2 plus V3, which makes sense, right? This is the total voltage, is V1, V2, V3. Okay, voltage total V1 and V2. It will always be added up together in a series circuit, guys. In a series circuit, the voltage will be distributed like this. But the current will be different now, guys. In terms of the current now, guys, current flows like water, right? I keep saying current flows like water. Imagine if there is like 3 amperes of current flowing here. These 3 amperes will go through this resistor. Means to say this guy will get 3 amperes, this guy will get 3 amperes, and this guy will also get 3 amperes. The amount of water that flows in will be the amount of water that flows out, right? It doesn't matter how rocky the path is, but the amount of water that flows in is going to be the same amount. And in fact, if I do real calculation here, this can't even be 3 here, guys. It's actually all just going to be 1. With accordance to my Ohm's law formula, guys. 1, 1, 1, 1 here. Because V equals to IR is still a thing, right? V equals to IR, V equals to IR. So all of them will get the same amount of current, regardless. Sorry? Yeah, current will stay the same because the current will flow like water. Doesn't matter how it flows, but ultimately it will just flow in and flow out, right? Same thing for this one as well. Even though this guy is the bigger resistor, it will still get 1 ampere, and this guy will still get 1 ampere because of the flow of current, guys. You will all need to know this, guys. Very, very important. And because of this, we can formulate our second formula. Current total is equals to current 1, which is equals to current 2, which is equals to current 3. Very straightforward for series. Don't copy anything first, guys. It's a very ugly drawing, and you have a better drawing later on. Understand the concept first. Then for total resistance, very straightforward in a series circuit. R1 equals to R plus R2 plus R3, right? So here we'll have a total of 9 ohms, and here also we'll have a total of 9 ohms, which will yet again be true for the ohmic, sorry, for Ohm's law as well. V equals to IR will be true, and the series circuit formulas will be true as well. Right? Very, very important. Okay. Then next part is, everyone understand this way? Okay. Next part is going to be the parallel circuit ones, guys. Parallel circuit will be a totally opposite one. Just now I said that series voltage is the piece of cake, right? In parallel circuits, guys, current is the piece of cake. In parallel circuit, current is the piece of cake. Meaning to say the current will distribute it will distribute evenly if they're all in the same resistors. For example, if let's say right now I have a circuit here, right, with like maybe, I don't know, 9 ohms, 9 ohms, and 9 ohms, right? If let's say I have 3 amperes of current that flows here, right now this 3 amperes will flow all the way until it reaches this intersection point, where it will allow 1 ampere to flow here and 2 amperes to flow downwards. These 2 amperes will flow until the intersection point once again, where 1 ampere will flow here and the other 1 ampere will continue flowing here. You can see that the current is actually being distributed right now, guys. And this 1 ampere will continue flowing here all the way until it reaches this intersection point, where it will combine with the 1 ampere once again, and here will once again become 2 amperes. Same thing for this one as well. I will combine with this 1 ampere and this will become 3 amperes once again. So you can see that the flow of current is being something like this here. So if the current is the one that distributes evenly here, then voltage must be the one that stays the same. If let's say I have 9 volts here, this guy will still get 9 volts, this guy will still get 9 volts, and this guy will get 9 volts also. This is true if they are all the same resistors. But what if they have different resistors? Let's say right now I have like one that is like 6 ohms and another one that is like 3 ohms. Okay. If let's say I have 3 amperes flowing here, how much current will flow here and how much current will flow here? If you think about it, how much do you think will flow? Online want to give it a wow guess as well. Guys, let me give you a hint now. I've said this last week before as well. Current will always flow the path of least resistance. Remember a few weeks ago we said that if let's say I have a light bulb here, right, and then I connect an ammeter here, will this light bulb light up? No. Why not? Because current flows the path of least resistance, right? The current will say that, oh, I find that here is much harder to flow than here. So because ammeters generally have very low resistivity, all the current will actually flow here and bypass the lamp, right? So there'll be 0 current flowing here, right? This is true if this thing here has very low resistance, right? Current always flow the path of least resistance. And if you can understand that concept, guys, thinking back here, how much current will flow in this 6 ohms and how much current will flow in this 3 ohms if I have 3 amperes? How much? 2 and 1. 1 and 2. Excellent. That is absolutely correct. Why? Because, like I keep saying, current flows the path of least resistance. These 3 amperes will reach this intersection point where it will detect, oh, there's a high resistance here. I'm going to let less current flow. Oh, there's a lower resistance here. So I'm going to let more current flow, guys. This is why, if, let's say, for example, I have 6 volts here, this thing here will still get 6 volts and this thing here will still get 6 volts because individually, the Ohm's law formula will still be in play, guys. You'll still see that V is equal to IR and V is equals to IR once again. Okay, everyone? And because of this, we can formulate our formula, guys. In terms of a parallel circuit, voltage total will be equals to V1 equals to V2 equals to V3. Voltage is the one that is equal right now. But the current, guys, is the one that distributes I1 plus I2 plus I3 here. You will see a pattern here, guys. If you look at the voltage and current formula of parallel circuits versus that is series circuits, guys, you see that in series, voltage is the one that plus, current is the one that is equals. But in parallel circuit, voltage is the one that is equals, and current is the one that is plus, guys. You'll see that they are exactly opposite of each other. All right, and then the final formula that I want to talk about in terms of a parallel circuit is essentially the resistance formula. The resistance formula is given as 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3. Right, meaning to say, guys, if I want to find the total resistance in this circuit here, it's 1 over 9 plus 1 over 9 plus 1 over 9. A lot of students make this mistake. Once they apply the formula already, right, they're going to tell me, oh, 3 over 9. the final resistance is 1/3. This is correct. Why not? Yeah, because 1/3 is only equals to 1/RT. In other words, in order to find RT, I have to flip both things around and I'll get a final resistance of 3 ohms here. This thing here has a total resistance of 3 ohms. You guys understand what I'm talking about? This part is important. Make sure you don't go trigger happy and then say this as the answer. Because this is sure as hell not the answer. And in fact, you need to flip it the other way around, guys. All right? This is formula, right? If I just substitute the 9 and 9 and 9 in, I'll get 1/9 plus 1/9 plus 1/9, right? Which is 3/9, right? Which is 1/3, right? A lot of students, they say this is the final answer already. They tell me that, oh, this circuit here has 1/3 ohms, which is not correct. Because according to the formula, this is only 1/RT. Right? Right. Which means to say, in order to find RT, I need to flip both things around, which is going to give me 3 ohms at the end of the day. This circuit here will have 3 ohms at the end of the day. Same thing for this one as well. If you see this next one here, this will be 1/6 plus 1/3, right? Which is going to give me 3/6. But this is not the final answer once again, because this is only equals to 1/RT. RT will need you to flip it the other way around and say that this is essentially just going to be 2 ohms at the end of the day. Understand this one here? Important. A lot of students, they give me the answer in fraction, which is absolutely wrong, guys. Do not leave your answer in fraction because that is only 1/RT. I want the total resistance, not 1/RT. 明白吗，大家？ Okay, if you all can understand what I'm talking about here, spend the next 3 minutes copying everything from this here. And always remember that series voltage is a piece of cake and parallel circuits current is a piece of cake.
It's like, current is the P. Voltage is
Series circuit current is a piece of cake. Is it bad? What is it put here? Hello. Je vais faire je vais Oh, please take a time to copy. Copy everything down, then you're done for the day. It doesn't match. For those who aren't copying, you can actually go already at this.
Okay, bye.
Bye, everyone. Okay, bye, Rachel. Switch. Give me a good reason. Is this your first time or your second time doing? First time before. Wow, what you saw first time so that you all right. You try a second time and see. Yes. It's on. I'm seeing. So.